What does it signify when a celestial wanderer appears to be breathing? 3 Atlas, a voyager from a distant stellar nursery, is expelling 40 kilograms of water per second into the frigid expanse, far removed from the sun's warmth to account for such a phenomenon. Savants are murmuring, it exhibits characteristics of being alive. However, the saga of this comet extends beyond this peculiar behaviour. It harbours unusual nickel devoid of iron, displays cyanide in its trailing plume, and hints at an origin dating back billions of years prior to our own planetary system. Meanwhile, removed from this cosmic interloper, amateur astronomers have uncovered the most extensive collection of anomalous radio signals observed to date. The celestial bodies Mercury and a specific planetary series have aligned with uncanny timing across the October firmament, sparking speculation regarding a potential connection to 3 Atlas. Concurrently, Blue Origin's October mission has generated more queries than definitive answers. Did this event even transpire? Remain with me until the very conclusion as we endeavour to unravel these disquieting questions, presented in our inaugural multi-narrative format, designed to keep our late-night audience fully informed of all celestial occurrences unfolding above us. If these enigmas have captured your attention as profoundly as they have mine, be certain to click like and subscribe to ensure you don't overlook any updates. As these revelations continue to unfold in real time, share your thoughts in the comments, indicating your location, the current time there, and whether you believe we are being furnished with the complete truth concerning these paradigm-shifting discoveries. And should you wish to contribute to the growth of this community, please disseminate this video across X, Facebook, Reddit, or even within your personal communication circles. It is your support that empowers us to continue pursuing narratives of this magnitude. Thus, we express our sincere gratitude for your unwavering backing. Part 1. The Unaccountable Emanation. Envision this scenario. You're adrift in the profound silence of the cosmos, situated more than 3 times the distance from the sun that our own planet occupies. In this remote locale, sunlight is but a faint caress. Ice remains perpetually frozen. Comets enter a state of dormancy. All existence appears to be in slumber, and then you perceive it. A comet, unmistakably expelling vast quantities of water into the void, showering 40 kilograms of this substance into space every single second. This is not a mere trickle, but a deluge. Water gushing from a frozen celestial body, a place where such an outpouring of water is utterly unanticipated. This is 3 Atlas, an interstellar comet that has traversed into our solar system from an unknown origin, bearing the cosmic laws of a different star's dominion. And these laws, they starkly deviate from our own. The initial indication arrived from SWIFT, a space-based observatory engineered for the detection of gamma-ray bursts. SWIFT directed its ultraviolet sensors towards 3 Atlas in early 2025 and detected an impossibility: a luminous halo of hydroxyl molecules encircling the comet. Hydroxyl, or OH, is the byproduct generated when solar radiation disintegrates water molecules. It represents the lingering echo of water's dissolution. The presence of OH signifies that water was recently present, and SWIFT observed an abundance of it. The quantities are truly astonishing. At a separation of 3.5 astronomical units from the Sun, 3 Atlas was liberating 1.35 multiplied by 10 to the power of 27 water molecules each second. This equates to 40 kilograms per second, every second. For perspective, this is akin to releasing the volume of a small automobile's worth of water into space each minute, at a distance where our solar system's comets emit merely a whisper. Comets indigenous to our solar system do not exhibit this behaviour, not in this remote region. So far from the Sun, they remain frigid, inactive, virtually inert. Water ice requires thermal energy to sublimate, transitioning directly from a solid state to a gaseous one without an intermediate liquid phase, and there is simply insufficient solar radiation at this distance to facilitate such an energetic process. Our comets await their closer proximity to the Sun before they awaken and commence the emission of gas and particulate matter into space. 3 Atlas evidently did not receive this directive. You may recall Oumuamua, the initial confirmed interstellar visitor. That object was as arid as bone. No water, no outgassing, merely a tumbling mass traversing our celestial neighbourhood. Utterly silent. Subsequently, the comet just 2019 Q4, Borisov, the second interstellar visitor, arrived. Borisov was indeed active, but its conduct mirrored that of our own comets. It adhered to the established pattern. Its behaviour was predictable. It was, in the most positive sense, unremarkable. 3 Atlas embodies neither of these characteristics. It appears animated in a manner that defies conventional understanding. It is broadcasting water into space where only silence is expected to prevail. And the paramount question occupying the minds of every astronomer who has directed a telescope towards this entity is remarkably straightforward. How is this possible? What conceivable mechanism could be driving this phenomenon? Is there an unknown form of ice present? One that sublimates at temperatures we previously deemed too frigid? Is the comet's internal core still retaining heat from its formation billions of years ago? Is its rotation inducing a peculiar focusing of sunlight onto concealed reserves of volatile substances? Or are there chemical processes occurring within that rocky mass that have remained entirely unknown to us? The water is merely the commencement of the enigma. 3 Atlas is also disseminating other substances, including cyanide, nickel and carbon dioxide in proportions that defy rational explanation. Each subsequent observation adds another layer to the unfolding mystery. Every spectral signature that emerges from the data represents an additional unanswered question. This is not merely a comet behaving erratically. This is a comet that appears to operate under an entirely distinct set of physical laws. Laws formulated in a different stellar environment under varied conditions and with divergent chemistry. And now it resides within our solar system, affording us an intimate view of processes previously unobserved. The primary concern occupying astronomers is this: if 3 Atlas is exhibiting capabilities beyond those of our native comets, what does this reveal about its point of origin? What manner of star system gives rise to comets such as this? What were the prevailing conditions within its nascent planetary disk billions of years ago? And most provocatively, is this comet simply anomalous? Or is it a harbinger conveying tidings of the universe's potential for diversity? Every instrument capable of observing this celestial body is currently trained upon it. Spectroscopy, photometry, polarimetry, all available tools are being deployed. Because 3A Atlas is not merely a subject of curiosity, it is a portal, a fracture in our comprehension. And through this aperture, we may glimpse something truly extraordinary. Part 2. Nickel unaccompanied by iron. Comets are expected to conform to established patterns. As they encounter increased thermal energy, metals are anticipated to sublimate from their surfaces. Iron and nickel are consistently observed together, akin to inseparable companions. The presence of one typically indicates the presence of the other. This represents one of the fundamental constants of the cosmos, upon which we have come to depend. However, 3 Atlas appears to have disregarded this cosmic convention. The Very Large Telescope in Chile, directing its spectrograph towards 3 Atlas, detected a phenomenon that defied logical explanation. Nickel emission lines were intensely pronounced within the spectrum, strong, unmistakable, and impossible to overlook. Conversely, iron was either entirely absent or registered at such a negligible level as to be virtually undetectable. Nickel without iron. It is comparable to observing smoke without any preceding fire. It is akin to discovering footprints without any accompanying body. Within our solar system, such a scenario is unprecedented. When a comet attains a temperature sufficient to liberate metals, iron and nickel are observed in predictable proportions due to their inherent co-location within the same mineral structures. They form concurrently through analogous processes. They sublimate at comparable temperatures. They are chemically bonded in ways that ensure their perpetual association. Yet 3 Atlas apparently originated from a celestial realm governed by different physical principles. At an approximate distance of 2.8 astronomical units from the Sun, astronomers detected nickel being emitted from the comet at a rate of approximately 5 grams per second. While 5 grams may seem insignificant, it is crucial to recognize that this emission is continuous, occurring second after second, with no discernible presence of iron. This is not an anomaly. It represents a discernible pattern. It signifies the comet conveying fundamental information about its composition. Several hypotheses have been proposed, none of which are straightforward. The initial possibility involves chemical fractionation. It is conceivable that in the environment where 3 Atlas originated, nickel became integrated into volatile compounds that readily vaporize, while iron was entrapped within refractory minerals requiring significantly higher temperatures for sublimation. Picture nickel availing itself of transport with volatile ices, while iron remained sequestered within rocky particles, thereby creating the observed decoupling. Another theory posits the involvement of organometallic compounds. On Earth, we encounter molecules such as nickel carbonyl, where nickel atoms bond with carbon monoxide. These compounds are volatile and evaporate at relatively low temperatures. If 3 Atlas formed in an environment rich in carbon monoxide and other organic substances, it is plausible that nickel became encapsulated within such molecular structures. Upon exposure to sunlight, these compounds decompose, releasing atomic nickel into the comet's coma, while iron remains bound within solid particulate matter. Then there is the factor of space weathering. Cosmic rays and ultraviolet radiation subject interstellar objects to bombardment for extended periods, spanning millions or even billions of years. Such sustained exposure can induce peculiar alterations in surface chemistry. It is possible that radiation processing has resulted in the formation of nickel-rich surface layers, while iron has been either buried or chemically modified. The nickel we are detecting might be a superficial layer, a rind altered by radiation that does not accurately reflect the comet's intrinsic bulk composition. Or, and this represents the most intriguing possibility, 3 Atlas may have coalesced in a stellar system exhibiting genuinely distinct elemental abundances. Stars do not possess uniform chemical compositions. Older stars originating from disparate regions of the galaxy, stars formed from nebulae enriched by varying types of supernova events. Each possesses a unique elemental recipe. It is conceivable that 3 Atlas originates from a location where nickel was more prevalent in proportion to iron than is observed in our immediate vicinity. Perhaps its progenitor star possessed an unusual chemical signature, and this peculiarity is now imprinted upon every molecule of this comet. However, caution is warranted in this assessment. Spectroscopic analysis is inherently complex. Detecting faint emission lines against a luminous background presents significant challenges. There are inherent limits to detectability. It is possible that iron is present but falls below the threshold of detection. Perhaps the iron emission lines are intertwined with other spectral features. It is also conceivable that we are observing at inappropriate wavelengths. As the comet approaches the Sun and its temperature increases, iron may begin to manifest. This would offer a degree of reassurance, signifying that the universe continues to operate within predictable parameters. But what if it does not? What if 3 Atlas reaches its perihelion, its closest point to the Sun, and iron remains undetected? What if the ratio of nickel to iron remains completely inverted compared to all our prior observations? Such a discovery would be revolutionary, indicating that planetary systems can produce comets with metallic chemistry so divergent from our own that our current models would necessitate a complete overhaul. This is the very reason astronomers are observing 3 Atlas with such intense scrutiny. Every observation constitutes a test. Every spectrum offers an opportunity to either reinforce our current understanding or to fundamentally challenge it. And at this juncture, 3 Atlas is contributing more to the latter than the former. Part 3. a comet that activates. Comets are generally expected to increase in brightness progressively as they approach the Sun. The underlying physics is straightforward. Enhanced solar radiation leads to increased heating, which in turn promotes sublimation and the release of gas and dust. This relationship ought to be linear, predictable, and largely uneventful. 3 Atlas, however, appears to have also sidestepped this predictable behaviour. Observers monitoring 3 Atlas have noted an anomaly in its coloration. Initially, the comet exhibited a relatively neutral hue, perhaps tinged with a slight reddishness, characteristic of distant icy bodies. However, as it drew closer to the Sun, it began to acquire a green luminescence. This was not a subtle shift, but a vivid, almost ethereal green that became undeniably apparent in photographic representations. This green coloration originates from 2 sources: cyanide molecules and atomic nickel. Both emit strongly in the green portion of the visible spectrum, and both began to intensify dramatically as the comet's temperature rose. The increase in brightness was not gradual but exceptionally pronounced, indicating that the emission lines were strengthening at a rate exceeding what simple geometric considerations would predict. When factoring in the distance from the Sun, one observes a 4-fold increase in solar radiation per square metre, a phenomenon governed by the inverse square law of physics. Yet 3 Atlas's emissions were escalating at an even more rapid pace. Something was being unlocked. A novel process was being initiated. Astronomers refer to this as switch-on behaviour. Imagine a specific temperature threshold. Below this threshold, a particular type of ice remains solid, contained, and dormant. Subsequently, as the comet crosses this temperature threshold, that ice begins to sublimate. The rate of gas production experiences a sudden surge. New emission lines appear within the spectrum. It is akin to flipping a switch. At one moment, the process is inactive. The next, it is fully engaged. And once initiated, it can escalate exponentially if there is sufficient material to sustain it. 3. Atlas appears to possess multiple such activation points. The emission of water commenced first, at 3.5 astronomical units, a distance already considered anomalous. Subsequently, the cyanide and nickel began to manifest, emitting a vibrant green hue as the comet further increased in temperature. Each distinct emission suggests the exploitation of a different volatile reservoir, a unique chemical environment reaching its activation threshold. One model that might account for this phenomenon involves extended icy grains within the comet's coma. Rather than all activity originating directly from the nucleus's surface, envision small ice particles being lofted away from the nucleus by escaping gas. These particles drift away from the comet, remaining cold and frozen. However, as they travel, they are increasingly exposed to solar radiation. Eventually, each individual grain reaches its own specific thermal threshold and begins to sublimate. This process creates a distributed source of gas, not solely emanating from the nucleus, but from a cloud of icy particles enveloping it. This could explain the supralinear increase in brightness and the sudden appearance of new emission lines. Another plausible explanation involves thermal fracturing. Comets are essentially composed of a mixture of ice and rock, often referred to as dirty snowballs. When one portion of the comet heats up and expands while another remains cold and contracted, internal stresses accumulate. Eventually, structural integrity is compromised, leading to fracturing. When ice cracks, it can expose previously insulated material. Suddenly, there is new surface area available for sublimation, and novel volatiles are released. The comet experiences a dramatic outburst. It is conceivable that 3 Atlas is fracturing itself as it heats up, revealing successive layers of frozen chemical compounds. Then there are the exotic ices. Water ice sublimates at one particular temperature. Carbon monoxide ice sublimates at a significantly lower temperature, while carbon dioxide falls somewhere in between. If 3 Atlas is structured in layers, much like an onion, with different ices present at varying depths or within distinct regions, then as it warms we would observe a sequential activation of these various components. First, the highly volatile substances would become active, followed by the standard volatiles, and ultimately the more recalcitrant materials. Each layer would peel back, akin to chapters unfolding within a narrative. This is not entirely unprecedented. We have observed comets within our solar system exhibiting unusual behaviours. Some comets experience sudden outbursts, escalating in brightness by factors of 10 or more overnight. Some comets disintegrate as they approach the Sun, succumbing to thermal stresses that overwhelm their structural coherence. Certain comets remain dormant until they reach very close proximity to perihelion, after which they erupt into significant activity. However, 3 Atlas is engaging in these phenomena on a timescale that deviates from our empirical experience. It is exhibiting activity at distances where it should be quiescent. Its activation is occurring in ways that feel almost intentional, and the anticipation is mounting. As 3 Atlas continues its inward trajectory, will additional activation points be triggered? Will we observe the emergence of new emission lines, new molecules previously unanticipated? Will the observed activity stabilize, or will it continue to accelerate? Each passing week brings fresh data and renewed surprises. This is not a predictable, consistently behaving comet. It is a dramatic unfolding occurring in real time. Part 4. Its point of origin. Every celestial object carries within its trajectory a narrative. Its future path provides insights into its past, and the trajectory of 3 Atlas is recounting a story spanning billions of years and thousands of light years. Its orbit is hyperbolic, a technical designation for an open curve, a path that does not loop back upon itself. 3 Atlas originated from interstellar space, executed a gravitational pass around our Sun, and will subsequently depart, never to return. Its eccentricity exceeds 1, signifying that this comet is unbound, a free agent, a solitary wanderer. It is merely passing through our cosmic neighbourhood. Astronomers have painstakingly traced its path backward by analysing pre-discovery images. Pre-discovery observation involves scrutinising archived survey data for images of an object captured before its significance was recognised. It transpires that 3 Atlas had been photographed on multiple occasions by automated survey systems. Some of these images date back to when the comet was 6.5 astronomical units away, still approaching, still cold and remote. By meticulously compiling these observations, astronomers have reconstructed its trajectory with increasing precision, and that trajectory points outward, back into the galaxy. However, not towards just any arbitrary direction. Orbital modelling, integrated with data from the Gaia Space Telescope, an observatory that has meticulously mapped the positions and motions of billions of stars, enables astronomers to formulate informed conjectures regarding 3 Atlas's potential point of origin. The findings are quite surprising. The galaxy possesses a discernible structure. Stars are not randomly dispersed. The majority of stars, including our own Sun, reside within the galactic disk, a relatively flattened plane populated by younger, metal-rich stars orbiting the galactic centre. However, there is also a galactic thick disk, comprising an older population of stars that traverse more inclined and eccentric orbits. These stars in the thick disk are vertically extended, spread farther above and below the galactic plane, and they exhibit distinct chemical compositions. They are older, having formed earlier in the galaxy's history, when a lesser abundance of heavy elements was present. They possess lower metallicity. 3 Atlas's trajectory suggests a possible origin from this thick disk. If this hypothesis holds true, if this comet originated from that ancient stellar population, then it could predate our solar system in age. Our solar system is approximately 4.6 billion years old. Stars within the thick disk can be 7 billion years old or even older. This implies that 3 Atlas might be carrying ice and rock from a period predating the very existence of our Sun. Consider the chemical implications of this. The gaseous nebula that collapsed to form a star in the thick disk 7 billion years ago contained fewer heavy elements compared to the nebula that gave rise to our Sun. Supernova explosions have progressively enriched the galaxy over cosmic time, seeding it with elements heavier than helium. The earlier stellar generations consisted almost entirely of hydrogen and helium. Subsequent generations, such as our Sun, incorporate a few percent of heavier elements. Stars within the thick disk represent an intermediate stage, containing some heavy elements, but in lesser quantities than observed in our solar system. If 3 Atlas formed within such an environment, its composition would reflect this reduced metallicity. There would be a lesser abundance of iron, magnesium, and silicon, all the rocky elements that constitute planets, yet there would still be ample volatiles present: carbon, nitrogen, and oxygen, locked within ices and molecules. Perhaps this explains the remarkably high ratio of carbon dioxide to water. Perhaps this is why the metallic ratios appear anomalous. It is plausible that this comet serves as a chemical fossil, originating from an era when the galaxy was younger and the periodic table was less populated. Naturally, certainty remains elusive. Tracing an object's path back through billions of years of galactic movement is an inherently challenging endeavour. Gravitational perturbations caused by passing stars and interactions with the galactic spiral arms all contribute to obscuring the precise trail. Nevertheless, the mere plausibility that 3 Atlas is older than our solar system is an extraordinary revelation. We may be observing a relic, a survivor, a time capsule from the ancient galaxy. And should we be able to pinpoint its stellar nursery, the cluster of stars that form together from the same gaseous cloud, we might someday identify its celestial siblings, other comets, or perhaps even planets ejected from the same system, now dispersed across the galaxy. 3 Atlas could be a single character within a message inscribed across thousands of light years, and we are only just beginning to decipher its meaning. Part 5. What travels with it? Comets are not merely inert accumulations of ice and rock. They function as celestial vessels transporting the molecular constituents of their birth environments. And 3 Atlas is carrying exceptionally peculiar cargo. We have already discussed the prodigious outpouring of water, 40 kilograms per second streaming into space from distances where such activity should be non-existent. That water, or rather, the hydroxyl fragments remaining after solar radiation disintegrates it, served as the initial indicator of this comet's unusual nature. However, water represents merely the beginning of the enigma. Carbon dioxide presents the genuine astonishment. Observations indicate that 3 Atlas exhibits an exceptionally high ratio of carbon dioxide to water. Within the comets of our solar system, water typically predominates. It is the primary volatile and the main driver of their activity. Carbon dioxide is indeed present, but it plays a secondary role. 3 Atlas inverts this established order. Scientific observations hint that 95% of the volatile compounds detected are carbon dioxide, with water vapour being present in smaller quantities. This composition seems inverted, quite unlike the cometary makeup typically observed closer to home. The unusual richness in carbon dioxide prompts inquiry. One plausible explanation relates to the comet's formation temperature. Carbon dioxide ice solidifies at warmer temperatures compared to water ice. If Comet 335I Atlas originated in a hotter sector of its protoplanetary disk, nearer to its nascent star, it might have preferentially assimilated carbon dioxide while shedding some of its water. Alternatively, the radiation field of its parent star could have been different, altering ices in ways our Sun does not. Another possibility involves the giant planets within that system, if any existed, migrating in a manner that agitated the disk, intermingling materials in unforeseen ways. Furthermore, the presence of cyanide, or CN, is noteworthy. Cyanide is a common component in comets, and is responsible for the characteristic green hue of many. However, in 335 Atlas, the cyanide appeared after the water, later in the temperature-dependent sublimation sequence. In comets within our solar system, cyanide and water typically emerge concurrently due to their similar sublimation points. The delayed appearance of cyanide in 335I Atlas suggests it might have been sequestered differently, perhaps trapped within organic molecules requiring additional energy to break down, or frozen in layers beneath the water ice. And then there is the matter of atomic nickel, emitting a green glow, isolated from its typical companion, iron. While this mystery has been previously explored, its significance warrants reiteration. Every element and molecule detected serves as a crucial piece of evidence. Volatiles offer insights into the temperature and pressure conditions during formation. Refractory materials shed light on condensation sequences and thermal processing. The ratio of gas to dust reveals the comet's structural integrity and its propensity to fragment. Now, let us address the most speculative yet intriguing concept, the panspermia hypothesis. This theory posits that life, or at least the fundamental constituents of life, can disseminate across the cosmos via comets and asteroids. Comet 335I Atlas possesses water, organic compounds, and cyanide, a key precursor in prebiotic chemistry. If one were to engineer a comet intended to seed a planet with complex chemistry, these ingredients would be precisely what one would include. However, it is imperative to state unequivocally that this remains purely speculative. There is no current evidence to suggest that 335I Atlas carries life, nor is there any evidence that any comet has ever transported life. The panspermia hypothesis is compelling and theoretically plausible, but it remains unproven and it faces significant scientific hurdles. The relentless barrage of cosmic radiation presents a formidable challenge. Over millions of years traversing interstellar space, high-energy particles relentlessly degrade complex molecules. Stellar ultraviolet radiation exerts a similar destructive force. DNA, proteins, and even simple amino acids are susceptible to disintegration. For life to endure an interstellar voyage, it would necessitate deep interment within the comet, shielded by substantial layers of ice and rock. However, complex molecules might indeed survive, not in the form of living organisms but as chemical fossils. These would be molecules synthesized in the comet's parent system, perhaps within a planet's atmosphere or on its surface, which were subsequently incorporated into the comet. Such molecules could withstand the journey if they possess sufficient stability and are adequately protected. Analyzing them could unlock information unattainable through other means. They might elucidate atmospheric chemistry from an alien world, or reveal metabolic pathways from an extinct biosphere. They could be messages encoded in carbon, nitrogen, and oxygen, awaiting decipherment. This prospect fuels the ambition of some scientists to intercept these interstellar travelers. The objective extends beyond mere terrestrial observation. It involves dispatching a spacecraft capable of matching their velocity, landing on them, drilling into their composition, collecting samples, and conducting in-depth analysis. The technological obstacles are substantial. Interstellar objects traverse space at considerable speeds, tens of kilometers per second. Intercepting one would necessitate a spacecraft already optimally positioned or possessing extraordinary acceleration capabilities. Nevertheless, the scientific rewards would be immeasurable: a sample from another star system, chemistry from a distant galactic quadrant, and answers to questions we are only beginning to formulate. Comet 335I Atlas is already billions of kilometers removed from the inner solar system. While we missed the opportunity to intercept it this time, its existence demonstrates the potential for such encounters and reveals the vastness of what lies beyond, igniting a deeper curiosity for further exploration. Part 6. Citizen scientists catching ghosts. Sometimes, the most significant discoveries emerge not from sophisticated algorithms or machine learning, but from the meticulous examination of data by human observers employing keen intuition. Occasionally, These insightful individuals are not professional astronomers. Consider the phenomenon of odd radio circles or ORCs. If the term is unfamiliar, it is not surprising, as they were only identified in 2019, making them remarkably recent discoveries in astronomical terms. ORCs are vast, circular formations observable solely in radio wavelengths. They are invisible to optical or infrared telescopes. When a radio telescope is directed towards a specific region of the sky, these structures become apparent. Perfect rings of radio emission, some spanning hundreds of thousands of light years, drifting in space like ethereal cosmic smoke rings. Their exact nature remains unknown. While the prevailing theory attributes them to galactic winds or shock waves emanating from supermassive black holes, the scientific community is still actively investigating. They are genuinely enigmatic, and their detection is challenging due to their faintness and their tendency to blend into the background radio noise. Automated detection algorithms often overlook them, as they are typically designed to identify point sources or compact objects, rather than large diffuse rings. This is where citizen science projects like the initiative known as Radio at Home become invaluable. This project enlists volunteers to visually scrutinize radio continuum maps, searching for anomalies that deviate from the norm. Participants are not looking for anything specific, they are searching for the unusual. In March of 2025, a volunteer flagged an extraordinary find. The object, catalogued as Region 346-9 5030, possesses a rather unremarkable designation, but an exceptionally intriguing characteristic: a pair of intersecting radio rings, two circles overlapping in the sky to form a figure-8 pattern. This represents the most distant and powerful ORC discovered to date, identified not by an automated algorithm or a professional survey, but by an individual volunteering their time to meticulously examine data. The discovery was made using low-frequency continuum maps generated by the Low Frequency Array, LOFAR, a radio telescope network distributed across Europe. LOFAR produces an immense volume of data, far exceeding the capacity of professional astronomers to analyze manually. Automated processing pipelines handle the majority of this data, flagging candidate objects based on parameters such as brightness and shape. However, these pipelines incorporate filters and thresholds, designed to identify expected phenomena rather than the unexpected. This is precisely where human pattern recognition proves indispensable. Our brains are exceptionally adept at discerning anomalies, at identifying structure within noise, and at flagging something as noteworthy even when a clear articulation of why remains elusive. The volunteer who discovered Region 500 did not need to possess a deep understanding of org physics. They simply needed to observe the image and recognize its peculiarity. And they were correct. This is not an isolated incident. Radio at Home has facilitated the identification of multiple anomalies. Another volunteer identified a colossal radio galaxy with a distinctive ring structure encircling it. Yet another discovered a ring situated at the extremity of a jet, a feature not predicted by theoretical models. These are objects that would have been lost within the overwhelming data stream had humans not been involved in the analysis. This observation extends beyond the realm of radio astronomy. We are entering an era characterized by an overwhelming deluge of data. The Vera C. Rubin Observatory, upon its operational launch, is projected to generate 15 terabytes of data nightly, accumulating at this rate for a decade. No team of humans can possibly examine all of this information, nor can any set of algorithms identify every anomaly. A combined approach is essential: machines for bulk processing, and humans to detect the unusual edge cases that defy existing templates. Returning to the case of Comet 335I Atlas, could a citizen scientist have detected its anomalies earlier? Might someone examining spectral data have identified the distinctive nickel without iron signature before professional astronomers? Or could an individual monitoring cometary activity have questioned its unusual activity so far from the Sun? Perhaps, or perhaps not. The fundamental point is that anomalies like Comet 335I Atlas benefit from the widest possible range of observational eyes on the data. While professional astronomers possess specialized expertise, training, and contextual knowledge, they are also subject to ingrained expectations, models they seek to validate, and time constraints. Amateurs and citizen scientists, conversely, bring fresh perspectives. They are not bound by preconceived notions of what should occur, and are thus free to observe what is actually transpiring. Numerous accounts exist of amateur astronomers discovering supernovae, identifying asteroids, and tracking variable stars. The Japanese amateur astronomer Minoru Honda discovered multiple comets and a supernova. The British amateur Andrew Gray was a co-discoverer of an unusual stellar outburst. These are not random occurrences, but rather exemplars of what can be achieved when passionate individuals, equipped with telescopes or access to data, dedicate themselves to careful observation of the universe. As telescopes increasingly inundate us with petabytes of data, citizen scientists may well emerge as the initial responders to cosmic oddities, potentially flagging the next interstellar comet, the next peculiar radio structure, or the next inexplicable phenomenon. Subsequently, professional astronomers would undertake follow-up investigations to elucidate the underlying physics. This represents a collaborative partnership, and like all successful partnerships, its strength surpasses that of its individual components. Part 7. Citizen Science versus Professional Gatekeeping. However, it would be disingenuous to portray this relationship as entirely harmonious and collaborative. A palpable tension exists. The embrace of citizen science necessitates managing a proliferation of false positives, where well-intentioned amateurs flag phenomena that ultimately prove to be artifacts or mere noise. Furthermore, some individuals, driven by conspiracy theories, interpret every data glitch as evidence of extraterrestrial signals, a concern that understandably preoccupies professional astronomers. The Royal Astronomical Society and other professional organisations have engaged in extensive deliberations on this matter. On one hand, citizen science effectively alleviates backlogs, enabling projects to process a greater volume of data than would otherwise be feasible. It fosters public engagement and cultivates enthusiasm for scientific endeavours. On the other hand, stringent quality control is paramount. A discovery is not considered definitive until it has undergone verification, cross-checking and peer review, processes that demand significant time and expertise. False positives present a genuine challenge. An individual flags an object as unusual. Astronomers dedicate days or weeks to its investigation, only to conclude that it is instrumental noise, a satellite trail, or a cosmic ray impact. This represents time that could have been allocated to pursuing genuine discoveries. The accumulation of false positives can lead to skepticism towards citizen reports, diminishing the signal-to-noise ratio and inducing fatigue. Confirmation bias is another significant factor. When individuals are predisposed to find something specific, they are prone to perceiving it even in its absence. This phenomenon affects professionals as well, but the mechanisms of training and peer review provide crucial checks. Amateurs may lack these safeguards and might perceive patterns in random data, convincing themselves of their validity. This is how claims of alien megastructures around Tabby's star or messages embedded within pulsar timing residuals emerge. Calibration and error margins represent further considerations. Professional astronomers possess the requisite knowledge to assess measurement uncertainty and discern statistically significant signals from noise. Amateurs may not, potentially reporting detections that are merely 1 sigma fluctuations, statistically insignificant in the broader context. Moreover, the issue of bandwidth arises. If a citizen science project garners excessive popularity, leading to a deluge of flagged objects, the professional astronomers responsible for follow-up investigations may become overwhelmed. Their capacity to investigate every report is limited, necessitating prioritization. which could inadvertently lead to genuine discoveries being overlooked due to their being buried within the sheer volume of data. However, it is important to note that these challenges are not insurmountable. They are obstacles rather than deal breakers. Training protocols can play a crucial role. By educating citizen scientists on data quality assessment, artifact recognition, and uncertainty estimation, the rate of false positives can be significantly reduced. Mentorship programs, where experienced amateurs guide newcomers, can help maintain established standards. Tiered validation systems, requiring multiple independent volunteers to flag the same object before it is escalated for professional review, can effectively filter out spurious detections. The opportunities presented by this approach are substantial. Crowdsourcing anomaly hunts allows for more exhaustive searches of extensive datasets. Cross-verification by numerous independent observers minimizes the likelihood of a genuine anomaly being missed due to an individual having an off day. Diverse perspectives mean individuals from varied backgrounds might perceive patterns that specialists overlook. Let us revisit Comet 335I, Atlas. Could a citizen astronomer have flagged its nickel anomaly at an earlier stage? The spectral data is publicly accessible, and anyone with appropriate software can download and analyze it. However, spectroscopy is a complex discipline, demanding an understanding of line identifications, wavelength calibrations, and signal-to-noise assessments, making it unsuitable for casual engagement. Yet, perhaps with dedicated training, guidance, and a collaborative community, an individual could have identified the oddity before it garnered widespread attention. The same principle applies to its water production rate. Light curves, which measure brightness over time, are frequently contributed by amateur astronomers. If these amateurs had been examining ultraviolet data from the Swift telescope and had been trained to recognize unusual activity patterns, they might have flagged the superlinear brightening of 335I Atlas. They might have noted, "This does not resemble a typical comet," before professional surveys confirmed its anomalous behavior. Historical discoveries initiated by citizen scientists substantiate the efficacy of this approach. The exoplanet transit method, which detects planets by observing minute dips in a star's brightness as a planet passes in front of it, has been significantly advanced by citizen scientists analyzing Kepler data. Projects such as Planet Hunters have led to the identification of numerous confirmed exoplanets. Amateur asteroid hunters have discovered near-Earth objects that eluded professional surveys. Amateur nova hunters frequently precede professionals in discovering stellar outbursts, owing to their nightly observations with modest telescopes, whereas professional telescope time is scheduled months in advance. The logical conclusion is not to replace professional astronomers with amateurs, which would be an absurd proposition. Rather, the conclusion is that both are indispensable. Professionals provide the profound expertise, theoretical frameworks, and rigorous validation. Citizen scientists contribute breadth of coverage, fresh perspectives, and a sheer multitude of observational eyes. This is not a competition, it is a partnership. And in this era of overwhelming data, it is an essential partnership. Part 8. The Coincidence Effect. October of 2025 presented an unusual celestial spectacle. Excellent viewing conditions for both Mercury and Ceres. Mercury, the solar system's innermost planet, entered a favourable evening phase, appearing bright and elevated above the western horizon shortly after sunset. Ceres, the largest celestial body in the asteroid belt, achieved opposition, meaning it was positioned directly opposite the Sun in the sky, thus appearing at its brightest and closest proximity to Earth. On social media platforms, connections began to be drawn. Mercury was visible, Ceres was visible, and now this peculiar interstellar comet, 335I Atlas, exhibited active behavior. Were these events linked? Was there some grand cosmic alignment unfolding? Could the gravitational fields of the solar system be somehow stimulating or amplifying the comet's activity? To be unequivocally clear, the answer is no. There is no causal relationship. Mercury's orbital path has no bearing on the outgassing of an interstellar comet. Sirius's position relative to Earth exerts no influence on chemical processes occurring billions of kilometers away. These are independent occurrences, coincidentally observable within the same time frame, and nothing more. However, humanity possesses an innate predilection for identifying patterns. We are biologically wired to do so. It is a survival trait. Our ancestors who recognized that certain berries induce sickness and that specific animal tracks indicated the presence of prey were more likely to survive than those who failed to discern such patterns. Consequently, our brains exhibit a hypersensitivity to patterns, sometimes to the extent of perceiving them where they do not exist. This phenomenon, known as pareidolia, can occur on a cosmic scale. Pareidolia is the perception of faces in clouds or voices in static, essentially pattern detection gone awry. This frequently manifests in relation to celestial events. Ancient civilizations interpreted planetary alignments as omens. The appearance of a comet during a battle was seen as a sign of divine displeasure. The congregation of planets in a particular sector of the sky signalled the birth or death of royalty. The year 1910 provides a pertinent historical parallel. This was the year Halley's Comet returned, traversing the inner solar system on its 76-year orbital journey. The public reaction was one of intense fear. Astronomers had detected cyanogen, a toxic gas, within the comet's tail. Newspapers published sensational headlines proclaiming, "Comet's poisonous tail will pass over Earth." Individuals purchased gas masks and some hermetically sealed their windows. There were even reports of suicides among those convinced the comet would bring about their demise. Naturally, no such catastrophic event occurred. The comet's tail is exceedingly diffuse, essentially a hard vacuum by terrestrial standards. The quantity of cyanogen that actually reached Earth was negligible and undetectable. The comet posed no threat. However, the coincidence of the comet's appearance with unrelated events, such as solar activity, political unrest, and earthquakes, fueled the widespread panic. People were drawing connections between disparate occurrences. We are observing a similar phenomenon now with Comet 335I Atlas. The comet is indeed unusual, exhibiting genuine anomalous behaviour. Mercury and Ceres happen to be visible concurrently, and thus narratives of connection begin to emerge. Perhaps the comet is being reactivated by some form of solar system resonance. Perhaps its trajectory is being subtly influenced by gravitational perturbations. Perhaps this entire sequence is part of a larger, yet-to-be-understood cosmic pattern. Astronomers have performed the necessary calculations. The gravitational influence of Mercury on an object located in the outer solar system is, for all practical purposes, negligible. Mercury is a relatively small planet, only slightly larger than our Moon, and it is situated at a considerable distance. Ceres is even smaller and exerts even less gravitational influence. The combined gravitational pull of all planets in the solar system would be insufficient to significantly alter the behaviour of 335I Atlas at the distances at which it is being observed. The comet's activity is driven by internal processes, solar radiation, and its inherent composition, not by the incidental position of Mercury in its orbit. However, factual accuracy often takes a back seat when compelling narratives emerge. The human brain craves stories. We desire events to be interconnected because isolated occurrences can feel random, chaotic, and devoid of meaning. If the comet's activity is linked to planetary positions, it implies order, predictability, and significance. Conversely, if they are unrelated, it suggests we inhabit a universe where peculiar events simply transpire sometimes, a notion that can be psychologically unsettling. Confirmation bias exacerbates this effect. Once one begins to seek connections, they become readily apparent. Mercury was also visible during a previous cometary discovery. Ceres was near opposition when another anomalous object was detected. It is conveniently overlooked that Mercury is visible multiple times annually, and Ceres achieves opposition every year. It is also disregarded that unusual astronomical discoveries occur with consistent frequency. The brain selectively filters out non-coincidental events, retaining only those that support the prevailing narrative. Social media amplifies this phenomenon exponentially. In former times, if one formulated a theory linking planetary alignments to cometary behaviour, they might share it with friends, who would likely dismiss it as nonsensical, effectively concluding the matter. Today, posting such a theory online instantly connects individuals with a shared perspective. Links, images, and charts illustrating alignments are exchanged. One person adds a new piece of supporting evidence, and another disseminates it further. Before long, a fully formed alternative narrative emerges, competing with the established scientific explanation. The core takeaway here isn't that people are easily fooled or naive. It's that coincidences carry significant weight, and our brains are not finely tuned to discount them. Given the vast number of astronomical occurrences happening constantly, it's statistically inevitable that some will align purely by chance. These chance alignments will feel significant, even when they lack any real meaning. This is crucial because it influences how individuals interpret unusual phenomena, such as the Comet 3 atlas. If one is already predisposed to believe in cosmic conspiracies or the importance of celestial alignments, then the comet's peculiar behaviour can be seen as evidence of something greater. Perhaps it's not a natural comet at all. Maybe it's artificial. It might be reacting to planetary signals, or it could be a component of a grand cosmic framework that remains beyond our current comprehension. And this leads us to an even more remarkable segment of this narrative: the mechanics behind hoaxes, conspiracy theories, and humanity's tendency to transform scientific enigmas into cultural legends. Part 9, October 2025. An update. Did it even occur? October 8th, 2025. Blue Origin's NS-36 mission. 6 passengers, 11 minutes aloft. One mystery flyer whose identity remained undisclosed until the landing gear touched down. The capsule ascended, breached the Kármán line, experienced weightlessness, began its descent under parachutes, and settled in the Texas desert. A success. Another faultless flight for the company's burgeoning space tourism enterprise. Their 15th crewed flight. A routine event. Almost. That's the official account. ABC News reported on it. Medium published an article. A select group of space journalists shared tweets about the mission. The identity of the mystery passenger was disclosed post-landing. It was a private individual who had requested anonymity during the flight itself, but was agreeable to being named afterward. Nothing particularly unusual about that. People frequently opt for privacy. However, here's where things become peculiar. The aspect that continues to puzzle those who closely follow spaceflight endeavours. The silence. The unnerving, almost suffocating absence of widespread coverage. No viral videos emerged. No trending hashtags appeared. There were no celebrity reactions, no memes, no TikTok analyses. A spaceflight. A commercial crew venturing to the edge of space. Something that, just a few years prior, would have dominated headlines for days. This mission barely registered a ripple. Consider that for a moment. 6 individuals departed Earth. They experienced zero gravity, witnessed the curvature of our planet against the vast blackness of space, and returned safely. That is extraordinary. It should be hailed as extraordinary. Yet the internet seemed indifferent. Social media moved on within hours. The story evaporated like mist. Why? Why such limited documentation? Blue Origin typically releases footage from inside the cabin. Beautiful shots of passengers floating, laughing, pressing their faces against the windows. Where were those images? Why weren't they disseminated across every news outlet? Why didn't the revelation of the mystery passenger generate widespread curiosity? Who were they? What was their motivation for seeking anonymity? These are natural inquiries, the kind that typically ignite days of speculation and public interest. Instead, an eerie quiet prevailed. It was as if the flight transpired in a void, not merely of space, but of public attention. And that void, that absence, begins to feel like a palpable presence in itself. The silence becomes more resonant than any official announcement could have been. Doubts begin to surface. Uncomfortable questions arise. Did this flight truly unfold as described? Were there indeed 6 passengers? Or was the manifest different? Was the mystery passenger a genuine individual or a fabricated element to account for the lack of pre-flight publicity? Did the capsule actually launch on October 8th, or was footage from a prior flight redated? These are the musings of suspicion, the hallmarks of conspiracy thinking, the mindset that perceives threats everywhere and trusts nothing. But occasionally, the lack of evidence itself feels significant. When something that should elicit a strong reaction is met with silence, one must inquire into the reasons. Let us contrast this with April 2025. Merely 6 months prior, Blue Origin conducted another New Shepard mission, and that flight ignited public fascination. Not due to a malfunction, but because of its prominent passengers. Katy Perry, Gayle King, the inaugural all-female crew. High-profile individuals with massive followings, the kind of passengers designed to generate headlines, and indeed, they did. However, not the headlines Blue Origin desired. Within hours of the live stream concluding, social media was ablaze with conspiracy theories. Individuals asserted the flight was staged. They meticulously scrutinized every frame of footage, searching for discrepancies. The behavior of hair in zero gravity became a subject of intense forensic examination. Did it float correctly? Did it move too rigidly? Was it genuine hair, a wig, or computer-generated imagery? The capsule hatch became another focal point. Someone claimed it opened differently than in previous missions. Side-by-side comparisons were posted, complete with arrows and circled details highlighting perceived anomalies. Wasn't the latch on the opposite side previously? Didn't the door swing outward before? Why does this appear dissimilar? Then the more outlandish claims emerged. Accusations of green screens, assertions that the passengers were filmed in a studio with simulated windows displaying pre-recorded footage of Earth, allegations that hands appeared artificial, too smooth, too plastic. Complaints about the absence of visible scorch marks on the capsule after atmospheric re-entry. Every minor detail was interpreted as evidence of deception. Journalists systematically debunk these claims. Hair behaves unusually in microgravity because gravity is absent, allowing it to respond to air currents, static electricity, and random movements. The hatch mechanism is identical across all flights. Camera angles and lighting can alter its perceived appearance. Reflections in visors distort perspectives. Scorch marks may not always be apparent, depending on factors like dust coverage at the landing site and camera resolution. However, these debunking efforts did not quell the theories. If anything, they seemed to intensify them. Those who were intent on believing the flight was fake interpreted the debunking as a deliberate cover-up. They delved deeper, unearthed more purported evidence, and constructed elaborate scenarios detailing how the alleged hoax was executed. The conspiracy theory became self-perpetuating. Now we have 2 flights, 2 missions, utilizing the same rocket and a fundamentally similar profile, separated by a 6-month interval. One generated an inferno of attention and skepticism, the other barely made a sound, and one must ponder. Which scenario is more indicative of suspicion? Part 10. Celestial Enigmas as Reflections. The cosmos continually presents us with unexpected challenges, with objects that defy categorization, signals that seem nonsensical, and phenomena that contradict our meticulously crafted models. And invariably, without exception, we undertake 2 actions. Firstly, we diligently strive to comprehend the scientific underpinnings. Secondly, we project our own interpretations onto these mysteries. Consider Oumuamua, observed in 2017. It was the first confirmed interstellar object to traverse our solar system, exhibiting a tumbling motion, a reddish hue, an elongated shape, and a discernible acceleration. While not substantial, this acceleration was measurable as it departed the solar system. Its trajectory did not conform to a purely gravitational path. Something was propelling it. Scientists proposed outgassing, even in the absence of detected gas emissions, suggesting the release of minor quantities of volatile compounds that generated thrust, akin to a faint comet. Alternatively, it might have been a hydrogen iceberg, frozen H2, which would sublimate invisibly. Another hypothesis was that it was a fragment from a shattered planet, its shape and spin influencing radiation pressure effects. However, a segment of individuals, including some scientists, proposed an alternative explanation. What if Oumuamua was artificial? Perhaps a light sail, a thin sheet of material propelled by starlight. This would account for its acceleration, and if it were artificial, it might be a probe dispatched by another civilization, engaged in exploration. Or it could be derelict, remnants of space debris from an ancient extinct alien society. The same pattern of interpretation occurred with Tabby's star, KIC 84628552. This star, within the Kepler field of observation, displayed peculiar dimming patterns, characterized by deep, irregular fluctuations in brightness, at times dropping by 20% or more. No planetary body could account for such a phenomenon. No planet is sufficiently large to obscure that magnitude of light. Furthermore, these dips were not regularly periodic, as would be expected from a planet's transit. Astronomers suggested the presence of dust clouds, swarms of comets, or debris from a planetary collision. However, one paper, with a hint of levity, posited the existence of an alien megastructure, a Dyson swarm. This hypothetical construct would involve millions of solar panels or habitats orbiting the star, collecting its energy and thus irregularly blocking its light as these structures moved. This concept, to some extent, aligned with the observed data: odd radio circles, fast radio bursts, and the Comet 3 atlas. Each mystery serves as a canvas onto which we project our deepest hopes and fears. Are we solitary beings in the universe? Is the cosmos indifferent or imbued with purpose? Are there other intelligences out there? And if so, do they resemble us? Or are they incomprehensibly alien? The psychological drivers here are potent. Pareidolia, the tendency to perceive patterns in random stimuli, plays a significant role. We discern faces in clouds, hear voices in static, and attribute intelligence to astronomical anomalies. This is not a matter of inherent stupidity. It is how our brains are wired. We are fundamentally pattern recognition engines, and we possess a bias toward identifying false positives. It is safer to mistake a shadow for a predator than to overlook an actual predator for a shadow. Compounding this is an existential yearning. We desire connection. We seek assurance that we are not the sole sparks of consciousness adrift in a vast, desolate universe. Every anomaly represents a potential opportunity, a possibility, a gateway that might unveil something extraordinary. And thus, we persistently push against those gateways with considerable force. 3 Atlas acts as a mirror. Within its luminous green coma, we see a reflection of our own innate curiosity, our deep-seated desire for meaning, and our hope that the universe is more wondrous and mysterious than we currently imagine. And perhaps it is. It is conceivable that one day we will encounter something genuinely inexplicable, something that compels us to revise our understanding of physics or to acknowledge that we are not alone. However, that day has not yet arrived. For the present, we have a comet, a peculiar comet, a fascinating comet, but most likely still just a comet, and that is sufficient, for even natural mysteries possess an extraordinary quality. Part 11. The Archive of Extraterrestrial Systems. Envision the galaxy as a colossal library, not a repository of books, but of celestial bodies, comets, asteroids, rogue planets that were expelled during the turbulent formation of planetary systems, and subsequently flung into interstellar space. Each of these objects serves as a message in a bottle, carrying information about the star system from which it originated. And on occasion, one of these bottles washes ashore on our cosmic beach. That, in essence, is what interstellar objects represent. Postcards from distant stellar nurseries. They are not alien in the sense of extraterrestrial intelligence, but rather alien in the sense of being foreign, distinct, and having formed under conditions dissimilar to those prevalent in our own solar system. Each one we detect provides a data point, a singular sample, and with a sufficient number of these samples, we begin to grasp the diversity of planetary system chemistries across the cosmos. The comets within our solar system exhibit a notable degree of uniformity. They coalesced within the same protoplanetary disk, from the same homogeneously mixed gases and dust, under the influence of the same stellar radiation field. While variations exist, with some being richer in carbon monoxide and others in water, depending on their location within the disk and the temperatures they experienced, they are fundamentally a family, akin to siblings or, at most, cousins. Interstellar comets, however, are strangers. They originated elsewhere, under different stars, within disks possessing distinct compositions, temperatures, and dynamical environments. To date, every single one we have observed has been unique. Oumuamua, it was dry, did not exhibit outgassing, possessed an unusual shape, and demonstrated inexplicable acceleration. It bore no resemblance to our comets, nor did it behave like them. If it was a comet at all, it was of a type we had never before encountered. 2I Borisov, rich in carbon monoxide. It exhibited fairly typical cometary behaviour, but with a gas-to-dust ratio suggesting a colder formation environment than most of our comets. It appeared somewhat familiar, yet subtly atypical, akin to a dialect of a language one already speaks. 3 Atlas, with water and carbon dioxide spewing forth at considerable distances, nickel devoid of iron, and cyanide appearing belatedly. Nothing about its behaviour aligns with our past experiences. It speaks a language we can barely decipher. 3 objects, exhibiting 3 drastically different chemical compositions. If we extrapolate from these observations, assuming these 3 are representative of the broader population, then the diversity of cometary compositions throughout the galaxy is truly astounding. Not all planetary systems produce comets akin to ours. In fact, it's plausible that most do not. Consider the implications of this. In certain systems, comets might be predominantly composed of nitrogen ice, similar to Pluto's surface. In others, methane could be the primary volatile. In systems harbouring more massive stars, the snow line, the distance at which water ice can condense, is situated further out. Consequently, comets might form in colder regions and carry different volatile mixtures. In systems with migrating giant planets, the protoplanetary disk becomes stirred, intermingling materials from various temperature zones, thereby creating comets with peculiar hybrid compositions. Could some comets contain molecules previously unknown to us? Molecules that are thermodynamically possible, but require formation pathways that do not exist within our solar system. Potentially, exotic organic compounds, unusual ices, or substances that would greatly excite a chemist. The universe is vast. The range of stellar masses, disk compositions, radiation fields, and dynamical environments is immense. Nature explores this entire spectrum thoroughly, and some of the resulting phenomena are bound to be extraordinary. Now, let us delve deeper. If life necessitates specific chemical building blocks, water, organic compounds, phosphorus, nitrogen, sulfur, then comets that lack these essential ingredients are inherently sterile. They cannot serve as seeding agents for life, nor can they deliver prebiotic chemistry to planets. It is possible that many interstellar comets are indeed lifeless. Perhaps Oumuamua was merely a barren rock drifting through the void. However, if even a fraction of these comets carry the requisite chemistry, that fraction becomes critically important. This is because comets are galactic wanderers. They traverse vast interstellar distances crossing light years, and if they transport organic molecules, amino acids, or even dormant microbes shielded deep within their icy interiors, then life's fundamental components could potentially disseminate across the galaxy. This concept aligns with panspermia, the hypothesis suggesting that life can be transferred between worlds via comets or asteroids. While controversial and unproven, it remains a possibility. And 3 Atlas, with its water, its organic compounds, and its cyanide, possesses the necessary ingredients. Not life itself, likely, but the chemical precursors that could lead to life if delivered to a suitable planetary environment. Every interstellar object we detect expands our observational sample size. Currently we have 3 such objects. In 10 years, we may have dozens. In 50 years, hundreds. And with each new detection, we will meticulously measure its composition, trajectory, and activity patterns. We will establish a statistical understanding of what exists beyond our solar system. It is possible we will discover that water-rich comets are common, that most planetary systems produce them. Or, conversely, we might find that our solar system is anomalous, that water-rich comets are rare, and that most systems generate dry, carbonaceous bodies. Either outcome promises to be profoundly fascinating. And perhaps, just perhaps, we will eventually encounter a comet exhibiting clear biomarkers, molecules whose presence is difficult to explain without biological origins, such as phospholipids, complex organic compounds with chirality, or isotopic ratios that strongly suggest metabolic processes. Such a discovery would be revolutionary, confirming that life originated elsewhere and that biochemistry is not a phenomenon unique to Earth. We have not yet made such a finding. As far as we can ascertain, 3 Atlas is not carrying life. However, it is carrying information, and information is the fundamental currency of scientific inquiry. Every interstellar visitor represents a gift, a free sample delivered directly to our doorstep. All that is required of us is to examine it closely enough. Part 12. Nickel, a messenger. Let us revisit that curious nickel anomaly, as it is more than a mere oddity. It is a clue, a chemical fingerprint. And fingerprints, as we know, reveal where an individual has been. Stars are colossal fusion furnaces. Nuclear fusion within their cores transforms hydrogen and helium into heavier elements. Carbon, nitrogen, oxygen, silicon, sulfur, and iron. When massive stars explode as supernovae, these cataclysmic events forge even heavier elements, including nickel. These elements are then dispersed into space, mingling with interstellar gas clouds, and eventually incorporated into newly forming stars and planets. However, the elemental composition of stars is not uniform. The abundance of heavy elements, a characteristic astronomers refer to as metallicity, varies significantly. Young stars, which formed recently from gas enriched by numerous supernova generations, possess high metallicity. Conversely, older stars, which coalesced when the galaxy was younger and fewer supernovae had occurred, exhibit lower metallicity. Both nickel and iron are products of supernovae, but their relative proportions differ depending on the specific type of explosion. Type Ia supernovae, which occur when a white dwarf star accretes matter and detonates, yield distinct nickel to iron ratios compared to core collapse supernovae, the explosive demise of massive stars. If 3 Atlas originated in a system whose initial gas cloud was enriched by an unusual combination of supernova types, its nickel to iron ratio might consequently be skewed. Current hypotheses suggest that 3 Atlas may have originated from the thick disk, an older stellar population. Stars in the thick disk generally have lower overall metallicity, but the ratios of different heavy elements can exhibit variations. If the observed decoupling of nickel in 3 Atlas reflects the composition of its parent stars, then this comet serves as a tracer, providing insights into galactic chemical evolution that are otherwise difficult to access. The reason for this is that while we can analyze stellar atmospheres spectroscopically, measuring their iron, nickel, and other elements, stars are immensely distant. Consequently, we can only study a limited fraction of them in great detail. Furthermore, we are unable to study stars that no longer exist, stars that lived and perished billions of years ago. However, comets originating from such systems act as time capsules, preserving the chemical conditions present at their birth. If we were able to directly sample 3E Atlas and analyze its isotopes, trace elements and mineral structures, we would be holding a fragment of a star system that could be billions of years old and thousands of light years away. We would be reading a history written in atomic particles. Now let us consider a speculative, albeit fringe, idea that circulates in certain circles. Could metallic anomalies, such as a high nickel content, be indicative of processed material? Not processed naturally, such as through thermal metamorphism, but technologically processed. If an advanced civilization were engaged in asteroid mining, metal refining, or the construction of celestial structures, they would inevitably generate waste products, slag, tailings, and exhaust fumes. Such material would exhibit unusual elemental ratios because industrial processes are inherently selective. For instance, iron might be extracted for construction purposes, with nickel-rich residue being discarded, or nickel might be utilized for a specific application, with all other materials being disposed of. If a comet formed within a debris disk containing industrial waste, it could incorporate these anomalous metals. Subsequently, after millions or billions of years, that comet could be ejected, embark on a long journey through the galaxy, and eventually arrive within our solar system. We would then detect the nickel anomaly and be left to ponder its origin. To be unequivocally clear, there is absolutely no evidence to suggest that 3E Atlas is artificial or contaminated by technological signatures. This notion resides in the realm of science fiction. The majority of scientists dismiss it outright, yet it is not physically impossible. And in the absence of a definitive natural explanation for the nickel-iron decoupling, even the most far-fetched ideas warrant consideration. The more plausible explanation likely involves prosaic chemistry, such as nickel existing within organometallic compounds, or fractionation occurring during condensation, some process we have yet to fully comprehend that operates under conditions prevalent in other star systems but are rare or absent in our own. However, this is precisely what excites me. Every comet carries a chemical signature, a barcode encoded in its elements and isotopes. By compiling a library of these signatures, by cataloguing the compositions of dozens or hundreds of interstellar objects, we can begin to map the galaxy. We could correlate chemical signatures with their trajectories. A comet originating from the direction of the galactic center might exhibit different elemental abundances than one originating from the outer halo. A comet from the thick disk could display age-related signatures. We could utilize comets as indicators of galactic structure and evolutionary processes. Imagine a future where interstellar objects are so commonplace and our detection technology is so advanced that we are cataloguing them by the dozens each year. Each object would undergo spectroscopic analysis. Each trajectory would be traced back as far as possible. Every celestial object's makeup is recorded, eventually revealing recurring characteristics. We've observed that comets originating from a particular galactic sector tend to be rich in carbon, while those from another are consistently abundant in water. This allows us to begin understanding the underlying causes. It's plausible that the carbon-rich zones fostered the creation of more low-mass stars, which possess distinct planetary disk chemistries. Conversely, perhaps water-abundant regions experience more supernova events, seeding the surrounding gas with oxygen. 3 Atlas represents the genesis of this comprehensive catalogue. Each entry, each data point, signifies a starting point, and the peculiar, unattached nickel serves as a potent reminder that every piece of data possesses an inherent narrative. Each elemental ratio functions as a crucial clue. With perseverance and meticulous attention, we can decipher these narratives and reconstruct the grand history of our galaxy. Part 13, The Unseen Population, 3 notable objects, specifically 2 I Borisov and 3 I Atlas, representing 3 confirmed visitors from beyond our solar system within a 7-year time frame. While this number may seem small, it's sufficient for statistical analysis, enabling estimations of the number of other interstellar travellers passing through undetected. Astronomers have analysed detection rates, survey coverage, and the observed traits of these 3 entities. They estimate that at any given moment, there are likely several interstellar objects within Jupiter's orbital path. These are small, dark, swiftly moving entities, largely invisible to most observational instruments. Our detection of these 3 is attributed to sheer luck, their proximity to Earth, their brightness, or their passage across the sky during favourable observational windows. How many have we overlooked? Potentially hundreds, even thousands. For every interstellar comet we successfully identify, it is probable that dozens traverse our solar system unnoticed. Some are too faint to register, others move too rapidly for follow-up studies. Still others appear in sections of the sky not actively being monitored. Detection is challenging but increasingly feasible. New observational surveys are being implemented, boasting unparalleled sensitivity and sky coverage. The Vera C. Rubin Observatory, currently under construction in Chile, is designed to systematically scan the entire observable sky every few nights, capturing images of everything down to incredibly faint magnitudes. This observatory will identify asteroids, comets, supernovae, and indeed any object exhibiting motion or change, including interstellar visitors. Projections indicate that the Rubin Observatory could detect as many as 1 interstellar object each month, possibly more. This equates to a minimum of 12 per year. Over a decade, this would yield well over 100 confirmed interstellar visitors, providing a robust statistical sample. This volume of data would be sufficient to draw meaningful conclusions regarding their compositions, origins, and populations. The Square Kilometre Array, a radio telescope network being established in Australia and South Africa, will also play a significant role. Radio observations are capable of detecting molecular emissions from even faint comets. The SKA could potentially identify interstellar comets that optical telescopes might miss. Space-based ultraviolet and infrared telescopes will be instrumental in capturing comets that are actively expelling material but are obscured when viewed in optical wavelengths. Each new instrument enhances our detection capabilities, improving our ability to perceive these faint, swift travellers. However, detection is only the initial step. Thorough study presents a separate challenge. Travelling at velocities of tens of kilometres per second relative to the Sun, by the time we pinpoint them, analyse their trajectories, and schedule follow-up observations, they are frequently already departing. Muamua, for instance, was already receding when discovered. We obtained a single clear observation before it faded into the distance, too dim for further study. 2I Borisov, however, we observed as it approached, affording us months for detailed examination. Telescopes globally were directed at it, providing spectra, light curves, and extensive data. This represents the ideal observational scenario. 3I Atlas was also identified relatively early in its trajectory. We are acquiring valuable data, but it will soon reach its closest approach to the Sun, swing around, and head back into the void. Once it departs, it will be lost to us forever unless we manage to intercept it. Proposals are actively being developed for dedicated interstellar object intercept missions. These involve spacecraft engineered for rapid deployment, powerful acceleration, and rendezvous with interstellar visitors while they are still within the inner solar system. The technical hurdles are substantial. Such a mission would require a spacecraft on constant standby, ready for immediate launch. It would necessitate advanced propulsion systems capable of matching the object's velocity. Furthermore, it would need sophisticated instrumentation for compositional analysis, structural assessment, and potentially sample collection. Yet, the potential scientific rewards are extraordinary. Imagine landing on an interstellar comet, penetrating its surface, gathering ice and rock from another star system, and returning it to Earth for laboratory analysis. The scientific insights gleaned from such material would be virtually boundless. We could ascertain precise isotopic ratios, shedding light on nuclear processes within the parent star. We could analyze complex organic molecules with a level of detail unattainable remotely. We could search for amino acids, essential for prebiotic chemistry, and perhaps even for fossilized microbes, should we be exceptionally fortunate. Even in the absence of life, we would gain an exquisite understanding of the chemistry present in alien planetary systems. Every molecule, every mineral, every isotope would serve as a vital clue. Some scientists are already formulating concepts for such missions, with preliminary budgets being proposed. This is not mere science fiction. It represents a tangible engineering challenge, demanding but achievable. Within 50 to 100 years, we might have catalogued hundreds of interstellar objects, successfully intercepted a dozen, and returned samples from half a dozen. This wealth of data would provide a comprehensive understanding of galactic comet populations, the diversity of planetary systems, and potentially the prevalence of life's fundamental building blocks throughout the galaxy. 3i Atlas offers a glimpse into this future, a preview of what lies ahead. It demonstrates that interstellar comets are not merely rare curiosities but are, in fact, common occurrences ubiquitous throughout the galaxy, carrying information that holds immense scientific value. The unseen population is out there, navigating the darkness, awaiting our discovery, and we will find them. Systematically, we will catalogue them, study them, and gradually piece together the intricate puzzle of planetary system formation, the variations in chemistry across the galaxy, and perhaps, just perhaps, the true prevalence of life. Part 14. When anomalies accumulate time 0.5 seconds. Let us broaden our perspective and consider the larger context, because 3i Atlas is far from the only perplexing phenomenon currently engaging the attention of astronomers. Far from it. We have odd radio circles, enigmatic rings of radio emission with origins yet unknown, fast radio bursts, millisecond duration pulses of radio energy originating from distant galaxies, their mechanisms still debated, T-Tauri stars exhibiting bizarre dimming patterns that remain incompletely explained, Muamua, an interstellar object displaying anomalous acceleration, and 3i Atlas, a comet with extraordinary water production and unusual metallic signatures. These are merely the most prominent examples. Dozens, perhaps even hundreds, of less publicized anomalies exist. Transient events that defy categorization, spectral features that should not be present, objects moving in ways that resist simple explanation. Astronomy is currently encountering a surge of phenomena that defy conventional understanding. This is a relatively new development. For the majority of the 20th century, astronomical data was scarce. An observer would direct a telescope at an object, capture a photograph or spectrum, and dedicate months to its analysis. Discoveries were infrequent, and anomalies were even rarer. When an unusual observation arose, it received intense scrutiny due to the limited availability of other research subjects. Today, we are inundated with data. Automated surveys generate terabytes of information nightly. Sky surveys catalogue billions of objects. Gravitational wave detectors record cosmic collisions. Radio telescopes continuously scan the heavens. We are detecting more phenomena than we can possibly investigate thoroughly. And with high-volume data comes a higher rate of anomalies. If one examines 1 billion objects, even if only 1 in 1 million presents an anomaly, that still equates to 1,000 anomalies. The majority will prove to be instrumental artifact data errors or misclassifications. However, some will be genuine discoveries, and their thorough investigation requires time. We are currently in an era where anomalies are outpacing theoretical explanations. We are discovering phenomena faster than we can comprehend them. This situation is both exhilarating and precarious. It is exhilarating because new phenomena invariably drive advancements in physics. The discoveries of pulsars, gamma-ray bursts, and gravitational waves all originated from unexplained observations. Anomalies are the crucibles where breakthroughs occur. However, it is also precarious because hype cycles can spiral out of control. Every anomaly is sensationalized, potentially representing a revolutionary discovery. Claims of alien megastructures, warp drive signatures, wormholes, or dark matter interactions frequently emerge. The media thrives on such narratives, and the public is captivated. Subsequently, in approximately 9 out of 10 cases, the anomaly is ultimately explained by mundane causes: dust clouds, instrumental noise, or misidentified known objects. The danger lies in the erosion of credibility. When individuals repeatedly hear about potentially extraterrestrial phenomena that are later revealed to be simple dust clouds, they may cease to trust scientists, concluding that science is merely speculative conjecture. Worse still, they might cling to the extraterrestrial explanation, believing scientists are concealing the truth. T-Tauri's star serves as a cautionary example. When the hypothesis of an alien megastructure gained widespread attention, the public became deeply invested. Social media erupted, and news outlets eagerly reported on it. When subsequent observations revealed wavelength-dependent dimming indicative of dust, not solid structures, significant backlash ensued. While some accepted the scientific explanation, others maintained that the scientists were mistaken or deceitful. Yet, here's the crucial point. T-Tauri's star remains an object of significant interest. The dust explanation does not fully account for all observed data. Long-term monitoring reveals complex variability. It is an unusual star, possibly encircled by a debris disk resulting from a planetary collision, or perhaps exhibiting behavior that we do not yet fully comprehend. It remains a scientific subject of great value, even if the explanation is not extraterrestrial. The overarching lesson is that anomalies represent opportunities. They compel us to refine our models, consider novel mechanisms, and challenge existing assumptions. Even when they do not lead to revolutionary breakthroughs in physics, they advance scientific understanding. Muamua's peculiar acceleration, even if ultimately attributed to outgassing, prompted scientists to more deeply consider sublimation at low temperatures, exotic ice compositions, and surface properties. This is indeed progress. 3I Atlas presents another such opportunity. Its water production challenges our understanding of volatile sublimation distances. Its nickel anomaly compels us to contemplate metallic chemistry in comets, a subject we have largely overlooked due to the absence of significant metallic emissions from our own comets. Its dominance of carbon dioxide raises questions about the conditions in protoplanetary disks of other star systems. When a sufficient number of anomalies are observed collectively, discernible patterns may begin to emerge. It is possible that odd radio circles and fast radio bursts are interconnected, both involving energetic outflows from galactic centers. Perhaps interstellar objects like Muamua and 3I Atlas represent distinct populations with differing formation mechanisms. It may be that the transient array of astronomical phenomena is revealing something fundamental about the energetic nature of the universe. Alternatively, these anomalies might be entirely unrelated, individual eccentricities that happen to coincide within the same few decades simply because we now possess the technological capability to detect them. Either conclusion provides valuable information. The key is to maintain a simultaneous balance of skepticism and wonder. One can be enthusiastic about an anomaly without asserting that it necessitates a revision of fundamental physics. One can explore intriguing possibilities without becoming rigidly attached to them. One can adapt their views as new evidence becomes available. This is where effective science communication becomes paramount. When reporting on 3I Atlas, responsible journalists and scientists should state, "This comet is exhibiting unusual behavior. We are investigating several potential explanations. Here is what we currently know." rather than sensational headlines such as "Alien Comet Defies Laws of Physics" or "Scientists Baffled by Impossible Object." The emphasis should be on nuance, though nuance often fails to generate clicks, and careful language rarely goes viral. Consequently, the hype machine continues to operate, transforming every anomaly into a potential revolution, thereby setting the stage for disappointment when a more prosaic explanation is eventually found. The solution is not to cease reporting on anomalies. Instead, it lies in honesty regarding uncertainty, in presenting multiple hypotheses, and in updating conclusions as evidence evolves. The public should be treated as adults capable of handling ambiguity, because they are. Most individuals understand that science is a process, that answers change over time, and that admitting "we don't know yet" is a perfectly acceptable response. 3i Atlas is one anomaly among a multitude, significant and fascinating, but not yet definitive proof of anything. It is a data point, a mystery, and an opportunity for learning. Regardless of whether its ultimate explanation proves to be a peculiar natural comet or something entirely unprecedented, the very process of studying it, testing hypotheses, and eliminating improbable explanations holds immense value. This process is the essence of science, and science, when conducted with integrity, stands as one of humanity's greatest accomplishments, particularly when grappling with phenomena that remain beyond our current comprehension. Part 15. Final Reflections. Alive, yet natural. We have now dedicated thousands of words to unravelling the mystery of 3i Atlas, an interstellar comet exhibiting water emissions in a region where water should not be present, glowing with green hues from nickel and cyanide, intermittently brightening and dimming as if deliberately controlled, and carrying chemical signatures from another star system, possibly from an earlier epoch in galactic history. Is it alive? In a poetic sense, perhaps. It is dynamic, undergoing transformation, and reacting to its environment. It is active when it should be dormant. Its behaviour seems intentional, even though we understand it to be driven by physics and chemistry, not conscious will. But alive in a literal sense? Almost certainly not. There is no evidence of biological processes, no metabolic functions, no reproduction, no mechanisms for information storage and transfer, none of the characteristics we associate with life. 3i Atlas is essentially a celestial body composed of rock and ice, heated by sunlight, releasing gas and dust in accordance with physical laws. However, these physical laws are producing phenomena we have never witnessed before. Water sublimation occurring at unprecedented distances from the sun, nickel emissions unaccompanied by iron, a dominance of carbon dioxide. Its intermittent activity suggests a complex internal structure or unusual ice compositions. Each new observation adds another layer to this intricate puzzle. So, what is it? The most probable explanation is that 3i Atlas is a natural comet formed under conditions significantly different from those within our solar system. It might have originated farther from its parent star, in a colder region where carbon dioxide ice is more prevalent than water ice. Its parent star may have possessed an unusual chemical composition, resulting in atypical metallic ratios. Space weathering over billions of years during its interstellar journey could have altered its surface chemistry. The organometallic hypothesis is particularly compelling. If nickel became incorporated into volatile compounds such as nickel carbide, this could explain the decoupled emissions. This would necessitate specific chemical conditions during its formation, which, while unusual, are not impossible. The theory of formation in a dense galactic disk is also persuasive. If 3i Atlas is approximately 7 billion years old, and carries isotopic signatures from an earlier phase of galactic chemistry, this could account for some of its peculiarities. Ancient ice, ancient chemistry, and ancient minerals, all preserved in the frigid environment of interstellar space, are now being revealed as the comet approaches the sun and heats up. Could it be artificial? Could it be a probe, a derelict spacecraft, some form of technological artifact? The evidence does not support such a conclusion. Nothing observed about 3I Atlas inherently requires a technological explanation. All its observed characteristics can be, or at least potentially can be, explained by natural processes. Invoking extraterrestrial intelligence is unnecessary at this juncture. However, let us entertain this possibility for a moment. If one were to design an object intended to survive an interstellar journey and remain detectable billions of years later, how would they approach it? A comet-like object would likely serve as a protective shell, shielding the payload with ice and rock. Unusual chemical signatures could be incorporated as markers, designed to stand out to anyone analysing its spectrum. Natural sublimation would then be utilised to reveal these markers as the object approached a star. This is purely speculative, and there is no concrete evidence to support it. Nevertheless, it is worth considering that if we ever encounter an artificial interstellar object, it might not initially appear artificial. It could present as a comet, an unusual one certainly, but one whose peculiarities could be plausibly explained by natural phenomena until a deeper investigation is undertaken. 3I Atlas. Is it such an object? Probably, almost certainly not. However, the very fact that we are posing the question is telling. It indicates that this comet's characteristics are sufficiently strange to stretch our imaginations, prompting us to consider possibilities we would typically dismiss. And perhaps therein lies its true value. Not whether 3I Atlas is natural or artificial, nor whether its chemistry is merely peculiar or genuinely revolutionary, but that it compels us to think. It challenges our preconceptions and reminds us that the universe is far vaster and more enigmatic than our immediate surroundings suggest. It highlights that nature has had billions of years and trillions of star systems to explore the full spectrum of chemical possibilities, and we have only just begun to survey what is achievable. Each interstellar visitor presents a challenge. It tests our models, our theories, and our understanding of what constitutes normalcy. And it is through confronting these challenges that we evolve. Oumuamua challenged our comprehension of cometary activity. 2. I. Borisov questioned our assumptions regarding carbon monoxide abundances. 3I Atlas, however, is pushing the boundaries on multiple fronts. Volatile budgets, metallic chemistry, activity distances, and compositional diversity. The subsequent steps are clear. Observe 3I Atlas as it approaches its perihelion, meticulously measuring all available data, spectra, light curves, gas production rates, dust-to-gas ratios. Search for novel emission lines. Monitor for the eventual appearance of iron or the persistence of the nickel anomaly. Compare these observations with theoretical models. Refine those models. Generate predictions. Test these predictions. And crucially, prepare for the arrival of the next interstellar visitor, as there will undoubtedly be more. The galaxy is teeming with these celestial wanderers, and our detection capabilities are improving annually. Each will present a new enigma, a fresh set of clues, and an expanded window into the formation and evolution of planetary systems across the diverse tapestry of stellar environments. Perhaps one day, we will intercept one of these visitors. We will land on it, drill into its structure, and retrieve samples. We will analyze its isotopes in terrestrial laboratories, study its minerals under electron microscopes, and examine its organic inventory for prebiotic molecules, thereby acquiring knowledge that is currently beyond our imagination. Until that time, we will watch, we will measure, and we will wonder, for that is our human nature. We gaze at the universe and pose questions. Why is this comet active so far from the Sun? Where did it originate? What can it teach us? These questions themselves hold value, even before we arrive at definitive answers, because questions are the genesis of exploration. 3. I Atlas journeyed from a realm light years away, across billions of years, bearing a message encoded in water, nickel, and cyanide. We did not solicit this message, and its full meaning remains unknown, yet we are listening, observing, and learning. In this act of learning, in this persistent endeavour to comprehend, we discover something that might be the closest approximation to life within this entire narrative. Not the comet itself, but us, curious, wondering, reaching out to touch something that originated from an impossibly distant location, attempting to decipher a communication from another world. The universe continues to dispatch these transmissions, cosmic postcards, messages in bottles, visitors from the void, and each arrival serves as a potent reminder that we inhabit a vast, ancient, and incomprehensibly rich cosmos. A cosmos that will perpetually surpass our understanding, continuously surprise us, and eternally present new mysteries. 3i Atlas is one such mystery, a single comet in an infinite expanse. However, it is now our mystery. And whether it is merely a fragment of ancient ice, or something more profound, whether its secrets yield readily or resist our scrutiny for decades, we will persist in our search. We will continue to question, and we will keep listening for what the universe endeavours to communicate. For this is the essence of being human, to observe something unusual in the night sky, and to refuse to avert our gaze, to demand answers, even when the universe remains silent, to discover wonder in a plume of water, molecules emitted at a rate of 40 kilograms per second, in the emerald glow of nickel that should not be present, and in a trajectory pointing back towards stars we can never reach. We are small. The universe is immeasurably vast. However, a dialogue unfolds between our world and that immense expanse, a silent exchange bridging our observational instruments and those far-flung celestial wanderers, connecting our inquiries with any potential revelations. This dialogue, a patient discourse unfolding over generations and across cosmic distances, is inscribed in the language of light particles, spectroscopic signatures, and the celestial ballet of gravitational forces. 3 Atlas communicated. We perceived its message and remained attentive, anticipating its subsequent pronouncements.